Hello and welcome to The Naked Scientists with me, Grey Jackson, and Kat Arney.
This week we're looking at symmetry and whether it holds the key to the theory of everything.
Plus, the leading headlines in science this week, including how whistled languages could be unique when it comes to brain activity, a new colour-changing material that could help identify head injuries, and the latest from Perth's Science Week.
The Naked Scientists podcast is powered by ukfast.co.uk.
First, when it comes to targeting cancer in the body, one of the biggest challenges is delivering drugs directly to tumours, killing cancer cells efficiently while avoiding damage to healthy tissue that causes side effects. Now, a new study led by Anirin Kennelly at the University of Sheffield reveals a novel way to guide immune cells loaded with cancer-killing viruses into tumours using the power of an MRI, or magnetic resonance imaging scanner.
There are viruses that have been designed that can actively attack tumour cells. One of the biggest problems is getting them to the tumour itself. Obviously, our bodies are going to fight viruses, and if you just inject them, the body will naturally fight the virus away. But what you can do is you can carry them inside a macrophage or a white blood cell that your body is inherent to your body anyway, and so will let pass freely, and it's kind of a Trojan horse therapy, it's been known as before. The only problem with this is that if you just do this naturally, if say I inject a few million white blood cells that have a cancer treatment in them, only 5% of them will ever reach a tumour site. And the initial ideas here were that you would magnetise the white blood cells, and then if you placed a small external magnet over the tumour, then the white blood cells, as they float around the body, the ion within them would be attracted to the little external magnet, and therefore they would stay in the region of the tumour. The only problem with this technique is that it's only useful for kind of superficial tumours, those on the skin, and they can really be easily removable with surgery anyway. What happens if the tumours are deeper within the body? And that's where the MRI system comes in. It's a giant magnet itself, and we can actually localize the field using the imaging gradients, so we can start to target tumours deep within the body.
So how do you make these cancer-killing cells magnetic?
So we place into the white blood cells tiny little iron particles that are already used as MR contrast agents around the world. And they just contain tiny little iron particles, and as we all know, iron is very magnetic. So that's the beauty of the research that we've been doing. The actual magnets exist in every hospital in the world. They're used every day in diagnosis. It's exactly the same hardware. We did not change the hardware in any respect. So this can just be an application of that hardware in a new way.
And I guess marrying this kind of tumour targeting treatment in an MRI scanner, you can see what's going on at the same time as well.
Yeah, that's the real beauty of the technique. As well as targeting the therapy to the tumour, we can look at the development of the tumour over time in a traditional way that we would use MRI anyway. So let's say a patient has to sit in the MRI scanner for an extra 10 minutes while their therapy is induced. And that's the real benefit of the technique, that MRI is already being used to assess whether tumours are in your body, and if we can find them, if the radiologist can find them, then he will know where to target to.
How have you tested it so far?
At the moment, the current study is concerning prostate cancer. Prostate cancer was induced within our mouse model, and we also looked at the metastases into the lungs. So we directed the therapy towards the lungs in some cases, and looked at whether it reduced the metastases of the prostate cancer.
How well does it actually work?
In the current study, we treated the animals with one session of magnetic resonance targeting, and it lasted between 30 minutes and 1 hour for each animal. And we noticed a marked reduction in tumour size over a 21-day period.
Where are we with this research? Is this the kind of thing that we could see in hospitals very soon?
So the study we've done at the moment is a preclinical study. It was done in mice, and a mouse is much smaller than a human. So the forces that we can generate in our preclinical system, we may be able to generate in our human system, and that would need more testing. We would also need to test kind of how long we need to do the targeting for and how often. So probably about 3 to 5 years, let's say, before we see clinical application of this in clinical testing.
Anirin Kennelly from the University of Sheffield, and his research was published in the journal Nature Communications.
Head injuries have serious consequences, but it's not often realised how severe these injuries are at the time. Symptoms might only appear later, after further damage has already been done. To get ahead of the problem, researchers have now developed a material that changes colour when a force is applied to it. If worn on sports or army helmets, a change of colour would indicate how serious a head injury was, enabling appropriate action to be taken immediately. Professor Xu Yang at the University of Pennsylvania, who led the team, explained more to Amy Goodfellow.
If you think about athletes playing in the football field or the soldiers at the battleground, oftentimes they get hit on the head or on the body. So we want to be able to detect the force so the medic or any of the person, the coach, they can look at the material, see the color change, then they can say, whether this person, the head has been hit by a force which is too strong.
So you could use this material in a sports field or in a battlefield to have on the helmet of a person, and this will enable us to know if they've been hit on the head, how hard they've been hit.
Yes, exactly.
When you apply a force to the plastic, by squishing it, for example, the underlying structure of the material changes. Just like when you squash a bit of paper in your hand, it deforms. Except, as this plastic deforms, the change in structure means it reflects light differently, thus changing the colour. Even better, you can choose a colour scheme. I like the idea of a traffic light system. A hard impact would cause your helmet to go bright red, whereas green would mean you could play on.
And so once the whole size and shape is changed, and light will be reflected differently, so that's why the color is being changed.
There have been materials made like this before, but what's different about yours? Why is yours special?
So other people have also made inverse opals. So typically they made a very squishy, soft gel, like a rubbery materials or hydrogels. So in this case, it's like you put your finger onto rubber, so you deform the structure. Once you remove the finger, the rubber will bounce back. So in this case, you won't be able to record the color because the color immediately returns to the original state.
Your material works at the right kind of forces that we would experience in a sports or military application.
Exactly.
You seem to have got this material quite well worked out. How long will it take to get this into a commercial application until we start seeing this on the shelves?
I think the material itself, the fabrication of the material is well established. What I think is the need for the research and development is correlating this deformation or color change to real brain injury. So that's a long way to go to demonstrate how we actually using those materials indicate how much damage the brain has received.
Professor Xu Yang from the University of Pennsylvania, and her work was presented at the American Chemical Society annual meeting earlier this week.
You're listening to The Naked Scientist with Kat Arney and Greer Jackson.
Coming up in the news, Google delays its open-sourced mobile phone and the curious case of whistled Turkish.
Getting the next generation involved in science is a challenge across the world, and this week Western Australia launched National Science Week with Perth Science Festival. The Naked Scientist rocked up to blow up a few hydrogen balloons, but also to have a look around. Georgia Mills caught up with one of the lead organisers, Christine Allen, Executive Officer for National Science Week.
National Science Week is a celebration of science and a showcase of the best of science across Australia for a week.
And what are you hoping to achieve with this festival?
I was wanting to get people out and about and hearing about science in their everyday life, and also seeing the explosive science, exciting science, and get people excited about science. I think getting scientists out from their labs and talking to the public is a really important thing, so that's what we've got going on today, because they're often doing things that have to do with our health. with our future and technology, and we have no idea about them because they're always very busy doing other things, publishing papers and doing their own science, and getting out and communicating science is sometimes a low priority. So this week is a real, and particularly this weekend, is a perfect opportunity for scientists to come out and talk about their science and why we need to fund science in general and technology and put lots of resources into that sort of thing.
My name's Kirsten and I work for the International Centre for Radio Astronomy Research here in Perth.
What are you guys doing here?
We're doing a lot of things, but my favourite thing we're doing is we're building stargazers with the kids.
Can I have a look at one?
Yes, of course. Come over here. So I have here a tube, and it is basically like a normal post tube that you use to put posters in the mail, and we've got some black cardboard over the end of it, and then we've poked holes to make a constellation. So this one is Orion, so if I hold it up to my eye and I look up at the sky, I can see Orion.
Right, so at the end of the tube someone's pierced a lot of holes. 2 of them are red in the shape. Is that the shape of Orion?
Yes, that's Orion. So we've also got cellophane that we can put over the ends and make some of the stars different colours. So this isn't accurate in terms of where the colours are. Someone's just decided they wanted to make those ones red. But we do have accuracy in the colours. So we don't have any green because there are no green stars. There's only blue, yellow, red and white stars. The blue ones are the hottest and the red ones are the coldest.
What's the aim of this, getting kids poking holes in tubes?
So it's to teach them about the constellations and the patterns of the stars that we use in astronomy to understand the sky. Also, we give them a map of the sky, a planisphere, so they can go home tonight and have a look at the real constellation in the sky and get an idea of what's above them and what astronomy is all about. Hoping to really spark that joy and love of looking at the sky and understanding the world around them, so maybe they learn more about science later on and even consider a career in it.
While most of the stalls there were aimed at getting people interested in science, some of them were trying to get people to do science. One such stall was trying to get people involved in something called the MicroBlitz project. I spoke to Professor Andrew Whiteley to find out more.
We're trying to recruit the general public to take samples of soil for us around the state of WA, and this is different to the way normal science works because usually obviously scientists will go out themselves and sample, but the WA size is so big, about 22 times the size of the United Kingdom. We actually encourage the citizens to actually go out and take the samples for us. The reasons why we're doing it, we actually want to look at what's out there in terms of microbial life. We're what we call microbial ecologists. Microbes are really important in the way the earth works, that agriculture production is heavily involved with microbes, rehabilitation, and generally also it's a biodiversity question. What microbes are out there and where are they? And we don't really know the answers to these questions yet. So essentially it's about doing a statewide survey, looking for these key pockets of microbial activity. Are there good microbes out there that are associated with, say, really productive agriculture? Are there bad microbes as well? And are there areas that we could improve based on a microbial map?
And how are you getting people involved in this? How are you getting them on your team?
Well, for example, like today, where we're actually at the National Science Week here in Perth, and we basically have a stand, and it's like a recruitment drive. So people come up and we talk to them about citizen science, and there's a real interest in Western Australia about preserving their environment and really finding out what's out there. Australians have a real go-getting spirit and actually really just generally interested in the environment. So it's actually quite easy to recruit the citizen scientists. So we talk to them about the project, we give them jelly snakes, which is always a good enticement. And also today as well, we're doing a DNA extraction practical. So the kids can come along and actually sign up for the project and do some extractions from strawberries of DNA. And we bought 150 this morning. I think we've already run out within about 3 hours. And the kids are having a great time seeing actually what DNA actually looks like. There's clear issues with young kids coming through science and actually taking it on as a future career. So this is a real good way of actually engaging them at a very young age and actually teaching them about the science and about the real world and the natural environment, and that there are great careers and opportunities in it.
So if you guys waited just a little bit, we'll get some sort of fluffy stuff, and that's the DNA that should be appearing. You just have to wait a couple of minutes.
Yeah, don't stir it.
Don't stir it. Don't mix it up too much. There you go.
What's your name?
Tilly.
Hi Tilly, what are you doing here today?
Looking at science stuff.
Are you having fun?
Yeah.
And what have you been doing on this stall? This looks really interesting. There's tubes of what looks like strawberry jam. What have you been looking at with this?
It's strawberries that we're looking at the DNA, and it's been put on my hand, and it's been disappearing onto my hand. Yeah.
Wow. And why have you been looking at the DNA?
Because it's cool.
I think science is cool because you could invent some stuff and you could have some fun. Because I remember going to Science, she said, this lady said science, the best thing about it is that you could also have fun with the things you build.
Georgia Mills reporting from Perth Science Festival.
In the last 7 days, Google announced they've been forced to delay their open-source modular phone, called Project Ara, until 2016 due to issues in its development. Peter Cowley, tech investor, joins us in the studio now to fill us in on the details. Hello, Peter.
Hello, good evening.
Good evening. So, a lot of jargon there. Open source, modular. What do all these words mean?
Yes, so open source is the concept of nobody owning the development or design and many people contributing to it. It's something that actually was around about 120 years ago when the car industry put together their patents and know-how and allowed everybody to use it. We've probably heard of open source software. Unix is an open source software platform which is used in many smartphones. But other things that may not know open source are Wikipedia. Some pharmaceutical companies have opened up drug designs to be open source. Scientific journals are becoming open source. And rather very controversially is an open source 3D printed gun.
Oh, wow. Okay. What about modular, though? What do we mean when we say modular?
Modular, in the terms of the phone, is that the backplane of the phone allows a number of different modules to be put on there, which would be the processor, would be the memory, the cameras, the battery, other things such as medical technology, different forms of speaker, perhaps a better speaker, 2 speakers, 3 speakers, all together on this backplane.
Okay, I see. And Google's Project Ara has combined both of these two elements together to make this all singing, all dancing phone, I see.
Exactly, yes. Well, within the constraints of the size of the phone. So what they've done is to have something which they're calling an endoskeleton, which is basically a chunk of metal with some electronics in it, which then allows the modules to be plugged in. And the current standard for them is 8 modules on the back side, which are things like the processor, etc., and 2 on the front, one of which, of course, is the screen itself. Putting this all together in a way that's going to be relatively cheap and robust and everything is obviously a very big task.
Why do we want modular phones? Why do I want to be able to take it apart and put it back together again?
A good question. In fact, the original idea behind it is not the modularity, it's to try and open up the smartphones to more of the globe. So at the moment, the rough numbers are there are 7 billion people on the planet, 1 billion have smartphones, 5 billion have feature phones, believe it or not, and only 1 billion don't have a phone. The idea is to move these 5 billion to have smartphones, which gives them all kinds of functionality, etc. The upsides are that you can upgrade your phone without having to throw something away, which will use less waste.
So if my battery started to get a bit rubbish,
or there's not enough memory, you don't have to replace your phone every 2 or 3 years or 4 years, so there's less wastage there. You can share modules, so we could, I could lend you my posh camera one, and you could lend it back again. You could lend me your speaker, etc. And also people can make their own bits. But the downsides are it will be a bit bigger because clearly you've got this backplane in the middle of it. It will almost certainly be a bit more expensive, which doesn't make much sense if you're trying to increase the numbers. And the certification, this is of making it work around the world, will be pretty complicated.
Because I suppose one of the big issues at the moment is all these different phones and things all take different charges, and it's annoying. And I'm also thinking about, I don't know, what happens if the backplate comes off too easily, but you want it to come off reasonably easily so that it can be, so you can change all the bits. So I suppose there's lots of things to be balanced out
Yes,
here.
I mean, the rumours of the last week or two were that they were having problems with the backplate. So when you dropped it, all phones have got to go through drop tests, vibration tests, etc., and that these things were pinging out. They've got something really clever called an electropermanent magnet, which effectively you put a little bit of electric current in there, and then it's in one state, and you put electrical current in again, and it then unclips itself.
Clever. So it's not like a button? Or
No, exactly. It just fits on there with a bit of... So it's controlled by the software to release it or not. However, those rumours, I think, are wrong, and it sounds like it's more like there's a bit more work to do and that they haven't actually released it yet. The most important thing, though, is whether there is really going to be a market, whether the price is right, whether it's just the early adopters and geeks will be buying it, or whether they can get the 500 million or billion out there.
Surely, though, over time, like with anything, it will just decrease in price as it becomes more available, though.
It will, but if you take any form of manufacturing, if you can make something standard all in one box, then you're more likely to produce it more cheaply if it's very standard. I mean, yes, you're right. If you didn't have a camera on it, you didn't have a speaker on it, maybe, which doesn't make any sense for a phone, etc., then clearly it would be a cheaper phone then. So.
I see. And why has it been delayed?
It's been delayed, as I say, because of the possibly these rumours that it doesn't withstand the drop test,
issue.
or it's because there's some other functionality we're wanting to add.
I see.
Yeah.
Okay, so what's the future of this? Is everything suddenly going to become open source and modular? What can I expect to
Yes,
see?
there is a general move towards that. People are wanting personalised products, personalised presents, all kinds of things where you can adapt them yourself. And as 3D printers come out of the business space into the consumer space, that will help as well. But there's a number of areas where open source is being used. There's an open source car, so you can build your own car using components, print your own components. There are drones, robots. There's a number of medical devices, so open source prosthetics. One of the ones that you might be interested in is open source houses. There's actually something called WikiHouse, which is a set of plans which are open source, which people download and then print your own house, which you can then put together. So you can actually build a 4-bedroom house in about a week with 2 people.
Can I think of this like a flat pack house?
It does sound a bit like a certain Swedish company might be producing it, but that's not the case.
And what's different about this? Is it got wires in the walls? Is everything sort of already built in?
No, the idea behind it is that
literally you can just put it out within a week.
Exactly.
Very
easy and then you can modify the design, etc. Add windows where you want to do, etc. Yeah.
Okay. And I suppose the other benefit of this is that by lots of more people using all these bits of technology and designing things themselves, actually you're encouraging them to, learn more things about it and get into technology and science subjects.
At the moment, there's a big stranglehold, particularly in mobile phones, with about 5 to 10 big manufacturers. That will release that stranglehold potentially by opening it right up to smaller companies.
Brilliant. Peter Cowley, thank you very much.
Thank you very much.
Tech Investor.
Thank you.
And finally, if you find yourself wandering through the mountains of northeastern Turkey, you might catch this sound on the breeze. Well, it's not any kind of bird, it is whistled Turkish, and it's actually a very unusual kind of language. Professor Onur Günterken from Ruhr University Bochum in Germany has found something even more special about this whistled language. Sam Mahaffey has been finding out more.
So whistled Turkish is a way to communicate in mountainous regions. It only exists in the northeastern pocket of Turkey and it's used in a few villages. The interesting aspect of it is that when you whistle, you can be heard in several kilometers away. But when you talk, you can obviously not be heard in that distance. So that means in mountainous regions, whistled Turkish is extremely handy to talk to neighbors that are on the other side of the mountain.
But whistled Turkish isn't a different language. It's just communicated in a different form. It's like how we can communicate English by speaking it or writing it, or how some people communicate by using Braille and sign language. Whistled Turkish has all the same grammar, words, and meaning as Onur's spoken Turkish. But like I don't understand Braille.
I do not understand whistled Turkish. The physical change from spoken Turkish to whistled Turkish is so radical, so vast, that only after a while, and if I knew the context, I could pick a few words, but that's it.
If native speakers can't understand Turkish in whistled form, can you tell that they're the same language? Let's try. If I wanted to ask for 1 kilogram of tomatoes in Turkish, I'd say
1 kilo domates lütfen,
which in whistled Turkish would be. I could say the Black Sea is beautiful.
Karadeniz çok güzel.
And how about we speak whistle language?
İslik dili konuşuyoruz.
But Onur has found something extraordinary about whistled Turkish. Whereas other forms of language are processed in one side of the brain, usually the left, whistled Turkish uses both sides. This is because it uses melodic changes to convey meaning, a bit like how we use intonation to express emotion.
So let's suppose you're calling up a friend in the evening and she says to you, "Oh, I'm so happy that you called me back." Or she may say, "Oh, I'm so happy that you called me back." It's the same words, it's the same syntax, but it has a completely different meaning. And this emotional content tells us a lot about the deeper meaning of a sentence. And this is encoded in what is called the melodic line, slow changes of the acoustic signal over time. And now whistles are exactly that, slow changes of the acoustic signal over time. So, and this is the speciality of our right hemisphere. So whistle language should be encoded and processed by the right hemisphere.
If the right hemisphere processes melodic changes, does it also process tonal languages, like Mandarin Chinese? Apparently not. In Mandarin, different intonation of syllables can convey totally different meanings, but scientific studies have shown that the left hemisphere is still dominant over the right. Honor thinks that this could be because of how fast these intonations occur.
Possibly still tonal languages have too many fast changes of the auditory signal, and so they fall into the mechanisms of the left hemisphere. There is no other language, to my knowledge, except whistle language, that has these very slow modulations over time.
These slow modulations are closer to singing than to tonal language. In singing, the melodic line varies over a whole phrase, making it better suited to the mechanisms of the right side of the brain.
The right hemisphere has a certain kind of superiority for the analysis of song and music and rhythm in general, so that, for example, people with a left hemispheric stroke who have major trouble to speak can sing, and they also sing with words. So there we see that the right hemisphere has a contribution under certain circumstances.
Dr. Gunterkun hopes that one day his findings will help in developing treatments for conditions affecting language.
Well, that would be my dream. Suppose we would have a patient from Kushköy, one of these villages where people use this whistled language. And this patient would, let's say, have a left hemispheric stroke and would be unable to properly understand Turkish in its spoken form. Would this patient suddenly understand more about what the other people say when we would deliver it in a whistled form? That could be an alternative route to language understanding.
And so, Onur Gunterkun, many thanks.
That was Sam Haffey talking to Onur Gunterkun from Bochum University in Germany, and his research was published in Current Biology earlier this week.
Now, on to the main theme of our show, symmetry. This is something I'm very familiar with, and I'm sure you are too, Kat. Whether it's checking that my eyeliner's uneven or making sure those photos are blue-tacked straight on the wall.
Well, you've done a good job on the eyeliner today, I have to say. However, there is much more to symmetry than meets the eye, and interestingly, it's been the guiding light for almost all of our modern physics theories. Scientists even think it could hold the key to finding a theory of everything, one equation that could explain how our entire universe works.
But before we get down to the nitty-gritty, why does symmetry appeal to us? Do we seek it out, even if it's not there? And if so, could it mean our assumptions and theories in physics are wrong? Ben Jones from the University of Glasgow explained just how he's investigated our attraction to symmetry.
There's really kind of two different types of studies that people have done to look at the relationship between symmetry and facial attractiveness. There's studies where people have measured symmetry in faces and had those faces rated for attractiveness. And in those kind of studies, you tend to see a sort of positive correlation. So more symmetric faces tend to be more attractive. But it's really quite a kind of weak relationship. But when you take a photograph of a person's face and then using computer graphic techniques manipulate it to be more symmetric, then you start to see slightly larger effects of symmetry. So making a face more symmetric tends to make it look more attractive. And if you take an individual face and then kind of exaggerate the naturally occurring asymmetries in it, it very quickly becomes unattractive and even can become really quite sort of bizarre and freakish looking.
Bizarre and freakish looking? I had a barbecue last night and decided to conduct my own analysis by showing my friends 3 pictures of one girl. In one, the image had been manipulated to look extremely asymmetrical. We call this number 1. Picture number 2 is what we might consider a normal face, a few asymmetries here and there. And number 3 was completely symmetrical. They, of course, had no idea why I was showing them 3 pictures of the same person, and it caused considerable debate when I asked them which one was the most attractive.
They're the same, but just slightly different.
Have they got a different crinkle because of the paper?
No, I think that's just my bad folding in my backpack.
The eyes, haven't they?
Yeah.
No, what?
What are you thinking? I can't tell.
I'd say middle.
Yeah, I'd say
You'd say middle is most attractive?
The more I look at it, 3 is becoming more
I
attractive.
think 3 is more attractive.
3 is more attractive?
Her eye's wonky on the side. There's bigger space.
One is nowhere near it.
Yes.
So one is the least attractive. We're agreed on this.
Yeah.
And there's more leaning towards 3.
I
think 3 looks like she's got bags.
I'd actually say 3 is the
I
least
think,
attractive.
yeah.
With 1.
I'm going with
You're going to say with 1.
loyal to her.
The more I look at this one, the more I go
I think
Number
middle.
2.
How many for number 1?
I don't like the mouth though of this one, so it's a bit frowned down.
For number 1.
So you're for number 1?
Yeah, I've got to now, and I've got to stay loyal now.
Okay.
I'll go with 1.
Number 2, who's for number 2?
Yeah, all over.
So we've got 3 for number 2. You're going to go for number 3. You've completely disproved all the science.
What's the science?
Okay, so the idea is, are we biased to seeing symmetry? Because we find symmetry more attractive. This is the most symmetrical one.
So I've got the best
This is
taste.
extremely asymmetric.
I've drank a lot of alcohol today.
My eyes are wonky anyway.
I think maybe we can rule this down to the fact that I've creased the paper too much in my backpack.
Yeah, it's a shame it goes right through.
And we're doing it in the dark.
Okay, so I'm not entirely sure what we can conclude from that extremely scientific investigation, but overall, my friends did seem to think the asymmetrical face was the least attractive. But why is symmetry so sexy? Ben Jones again.
Well, it's kind of quite a controversial issue, and there's a number of different theories that have been put forward. If you speak to sort of cognitive psychologists, they'll tend to point to the fact that we kind of develop an internal prototype of faces based on all of the faces that we encounter. But that internal prototype, which you can kind of think of as the mathematical average of all the faces that you encounter, is likely to be perfectly symmetric because all of those individual asymmetries in the individual faces that we see will all kind of average out. And we know that faces that more closely resemble this prototype are easier to process, and we might even like them more because that they're easier to process. And it's that kind of processing bias that could contribute to the appeal of symmetric faces. On the other hand, working from kind of ideas about animal behaviour, and particularly studies of mate preferences in non-human animals, other researchers have theorised that our attraction to symmetric individuals might be less to do with kind of processing biases and more to do with the type of qualities that symmetry might kind of advertise about people. So one idea is that more symmetric individuals might be healthier, they might be physically fitter, they might be physically stronger. And those are kind of characteristics that we find desirable in potential mates and also in potential kind of allies and associates.
I see. And are we biased to then see symmetry elsewhere?
It's certainly the case that symmetry isn't just attractive in faces. I mean, there's quite good evidence now that symmetry tends to be preferred in abstract art, at least among non-sort of professional art critics. And there's even evidence that symmetry might be attractive in things that you can't even necessarily see. So, for example, although when we think about symmetry predicting attractiveness in humans, we tend to think about symmetry of bodies and symmetry of faces, but actually the voices and even the body odours of symmetric people tend to be more attractive than those of relatively asymmetric individuals. And that kind of ties back again to this idea of symmetry perhaps being attractive because it advertises something about our kind of underlying physical qualities.
Ben raises an interesting issue. If we really do love symmetry, then are we biased to it? Do we see symmetry even when there's none? And could this have big implications for when we think about the theory of everything?
To find the answer to that, we need to delve into the world of maths. Now, we've just heard from Greya and her friends that when we think about symmetry, maybe we think about faces, two sides of a face matching up, or a yin and a yang, a mirror image. But when mathematicians think about symmetry, it's maybe not quite as simple as that. And to explain more, we're joined now by Mark Ronan. He's Professor of Mathematics at the University of Illinois in Chicago and UCL. Hi, Mark.
Hi there.
So, as a mathematician, how do you see symmetry?
We come at it from different directions, but it can all be explained by
taking an object like a square and looking at the different symmetries that it has. Not just a left-right symmetry or a top-bottom symmetry or a diagonal symmetry where you can reflect it across the diagonal, but there are actually 8 different symmetries for a square.
So that means that you could, say, put a mirror in the middle of it and it would still look like a square or still look the same from all these kind of different angles.
That's right. And the whole idea is to take all of them together, and that is what mathematicians call a group.
So that's a number of different kind of equal things, equal views of something.
Yes, you can look at it that way. And the idea is that you can do one and then another one, and the concept of a group is absolutely fundamental. That's what physicists use when they are talking about symmetry. They're really talking about a group of symmetries. And the word group was originally introduced in French, it's got an E on the end, but it's the same word, by Évariste Galois, a young mathematician who never reached his 21st birthday.
In terms of his contribution to maths and symmetry, what was Galois thinking of?
What he was doing with mathematics was he was trying to solve a problem about equations.
And what was that problem?
The problem was how to distinguish equations that have solutions that you can extract in a relatively simple manner and equations that have solutions you can't extract in a simple manner.
So these are kind of beautiful solvable equations and then more complicated, maybe insoluble equations.
It's a good word, because actually mathematicians use that word solvable. They're solvable equations and other ones that aren't solvable in the same sense.
And in terms of symmetry, which ones are the symmetrical ones?
The more symmetry they have, the harder they are to deal with.
So is this because you kind of look at the equation and it all sort of balances out? They're all more equivalent, more symmetrical, and it's harder to pick out, OK, we can start here, this is an answer.
That's absolutely right. You can't quite grapple with the thing very well because everything looks the same from different, multiple points of view.
A lot of what we talk about in physics is all based on equations, coming up with equations that describe the physical laws of nature. In terms of symmetry, how symmetrical are the equations that we have in physics?
Well, it's not so much actually solving equations, it's symmetry produces patterns. And physicists study patterns of different elementary particles, for example. When I was a teenager, there was a whole zoo full of these things. They managed to create order out of it, and they did it by using symmetry. In fact, Hermann Weyl, who was a famous mathematician, also a very good physicist, said, "Symmetry, as wide or narrow as you may define its meaning, is one idea by which man, through the ages, has tried to comprehend and create order, beauty, and perfection." But they came up with some very clever ideas using symmetry in a serious way. I don't just mean in a silly way.
In a sort of a matchy-matchy, this particle is the mirror image of this one.
It's not just mirror image. The symmetries were more complicated than that when they start to look at the standard model of physics. At the very most basic level, where you're looking inside an atom.
So broadly, when we're thinking about equations that govern the universe, govern how it works, should we expect them to ultimately have symmetry within them?
I think we probably ought to expect some symmetry, because if we don't have any symmetry at all, we're not going to make sense of things. Physicists really demand a lot of symmetry in order to make their theories comprehensible.
Thank you very much. That's Mark Ronan from the University of Illinois in Chicago and UCL.
This is The Naked Scientists with me, Gray Jackson, and Kat Arney.
Later in the show, we will be discussing what exactly do we mean by a theory of everything and how are we going to go about looking for one.
But first, we need to think about where we've got so far. We now know what symmetry is, but not how it's used in physics. All of our modern theories are based on these mathematical ideas of symmetry, including Einstein's famous ideas of relativity. But how and why is this the case? James Farr dragged me out of the office with a tennis ball to explain.
Einstein's theories completely revolutionised the way we think about gravity. And they were all sparked off by a simple fact which Einstein noticed about the speed of light, which we're going to think about now.
Okay, so what's this got to do with a tennis ball, though?
Well, the normal way we think about speeds is they add up in a very simple way. And to demonstrate this, if you can now go and stand about 10 metres or so away from me, Greer.
Okay, about 10 metres.
And if you can now throw the ball to me, not too hard, of course.
Okay, so I'm going to do an underarm throw. Ready?
There we go. That took about a second, say, to get to me. So we can say it was travelling at 10 metres per second. We both agree on that, right?
I'd say so, yeah.
So if we do this again, this time you're going to be running towards me as you throw the ball.
Okay, I'll give you my best cricketer's throw, okay, ready?
Go for it. Oh, that was much faster that time.
Sorry, Jack.
That was quite all right. So the ball was much faster because you were running as you threw the ball. So you can add the speed you were running at, maybe 5 metres a second, onto the speed you threw the ball at, because you threw it just as hard as you did before. So we add 5 plus 10 to get about 15 metres a second. That's the overall speed of the ball relative to me. How did the speed of the ball look relative to you?
Well, it didn't really feel or look any different to me.
Yeah, you threw the ball exactly as hard as you did before, so it should be the same speed. So here we've got a demonstration of two different observers, me and you, Greer, observing the same ball, but thinking that it's going at two different speeds.
Okay, so the movement of that ball is relative to us, you could say.
Exactly, and that's what's so different about light. If you were firing a beam of light rather than throwing a ball, the little photons which make up the beam of light would all seem to be moving at exactly the same speed, both from my perspective and from yours, even though you're moving relative to me.
Good to know, just in case I go throwing balls of light anytime soon.
Balls of light aside, this idea that light must always appear to travel at the same speed, no matter how fast or in what direction we're travelling, was Einstein's stroke of genius. He realised this by looking at the symmetries in the equations that describe light, as Daniel Baumann from the University of Cambridge explained.
One way of noticing that there's something symmetric going on is to notice that there's something that's not changing. If you look at the symmetric objects from different points of view and they look the same, that's how you identify that an object is symmetrical rather than arbitrary. And so here there was also a hint that there was something that didn't change. Two different observers moving relative to each other would agree on the speed of light. And so underlying this, there's a hint that there's a symmetry that enforces this. And so that symmetry is what's called Lorentz symmetry or Lorentz invariance.
These so-called Lorentz symmetries aren't actually too complicated. If you can imagine trying to measure the distance between 2 points on a piece of paper, then no matter how much you rotate your piece of paper, that measurement will always stay the same, right? It's sort of the same for light, in that the speed of light must always be the same for every observer, which means that there must be some kind of underlying symmetry. But how do we know that this is true?
To a theorist, you know it's true because it's too beautiful not to be, in some sense. I think even Einstein once said, if an experiment came out that would disagree with his theory of relativity, both special and general, then it's too bad for the experiment. There must be something wrong with the experiment because the theory itself is too beautiful to fail. But of course, at a practical level, we do have now plenty of experiments that just show us that this is really what's happening.
How has this had an effect on physics?
One way, especially for theorists, I think, it has demonstrated the power of pure thought in coming up with physical theories. So Einstein famously introduced these thought experiments, asked himself, what happens if I rush after a light ray, or what happens to time when a clock is traveling on a fast-moving train, and things like that. So it's a very different way of doing physics, less driven by experimental data, but by just purity of thought. And symmetries, and trying to see how the power of symmetries actually restrict the types of physical laws we can be writing down. And so this attitude of letting yourself be guided by symmetry has become vital. And I think Einstein was one of the first. And then, of course, at a practical level, it has just permeated all of modern physics. A world without relativity, to me, is unimaginable.
We've heard about how symmetry is used in our theories of relativity, which we use to describe gravity. This is useful if we want to think about very big things, like planets moving around the sun, but what if we want to zoom right in and look at much smaller things, maybe atoms? I'm going to head across the road from the Institute of Astronomy, where I'll get to the Cavendish laboratories. Historically, these labs have played a very important role in the build-up to what we now call the Standard Model.
I'm Professor Andy Parker. I'm the head of the Cavendish Laboratory. So the Standard Model is our current understanding of all the particles and forces between them that make up atoms or normal matter and indeed everything in the universe. So we have quarks, which are the constituents inside protons and neutrons and therefore make up the atomic nucleus and the bulk of the weight of the atom. And then outside of that are electrons, which circle the nucleus like little planets, and a bunch of other particles similar to electrons. And those two types of particles make up the matter in the Standard Model, and then the forces between them make up the interactions.
However, the journey to this theory was by no means an easy ride.
When we first turned on large accelerators, we started to make new particles by colliding things, and those new particles were coming out sometimes once a week. One was discovering what seemed to be a new fundamental particle, and people were talking about a zoo of particles.
The trouble was, it wasn't what you might expect from a zoo. There was no plaque telling you which species was which, and everything was mixed in together, lions with toucans and kangaroos all in one enclosure. Scientists needed a way to categorise these new particles, a bit like a zoo has a reptile house and an aviary. The Standard Model has helped us to do this using symmetry, and more recently, the Higgs boson, the particle which explains why things have mass.
In fact, the Large Hadron Collider, which discovered the Higgs, has just restarted and we're collecting data right now. And with the LHC data, we should be able to perhaps discover something really exciting.
Could potentially be very exciting indeed. James Farr reporting there.
So that's two very symmetrical theories about the world that work. But if we've managed to compress all of physics into two theories, can we go one further and squeeze it all into one theory to rule them all? In other words, can we get to a theory of everything?
Catherine Fries is the director of the Nordic Institute for Theoretical Physics. She joins us from Stockholm now. Hi, Catherine.
Hi, Greya.
What exactly do we mean when we're trying to make this theory of everything? What are we trying to do?
Well, from a physicist's perspective, a theory of everything is one that would encompass all the physical laws of nature. In today's universe, we know there are 4 separate forces.
When you say 4 forces, what are you referring to?
Well, we have the most important ones of our everyday lives. There's the electromagnetic force, so which includes electricity and magnetism. Then we also have the strong force. This is actually what holds our nuclei together. Our nuclei have neutrons and protons in there, and they don't fly apart because of the strong forces holding them together. So they're really necessary for our existence. We also have a third force, the weak force, which is responsible for many types of radioactivity. And then, of course, there's gravity. So today in the universe, we have all these 4 different separate forces.
And then at the Big Bang, when the universe began, we thought all these forces were one force, one single thing.
Well, as we go backwards in time, then we can watch them start to unify. So we do know that electromagnetism and the weak interactions unified into one single force, electroweak. And then as you go farther back in time, then you could also bring in, at least we think we can combine that with the strong interactions into what we call a grand unified force. If we could go even farther back in time, almost all the way back to the Big Bang, that's where gravity would join, if only we knew how to do that. That's what is really missing in our trying to build a theory of everything.
Why is that so tricky? Why can't we seem to unify? Is it just that we can't look that far back in time?
Well, that's certainly part of it. So on the theory side, there's a real stumbling block that, well, Einstein was already trying to get at it, and we've made some progress, but the unification of gravity in general relativity and then quantum mechanics, unifying general relativity and quantum mechanics, we don't know how to do that. We do have some ideas. If only we can make that work, then we have some chance of approaching this theory of everything.
So in some sense, it's joining this quantum world, the tiny world, with the much bigger world, these theories of gravity and Einstein's theories of relativity.
Yeah, the quantum world describes very well what's going on in atoms and then in the particles inside the atoms. It works on small scales. And general relativity, we know how to use it on the large scales of clusters of galaxies, the Earth, and things like that. But combining these two has proven to be very, very tricky.
Just stepping back a bit, what has this got to do with symmetry?
if we can, in fact, unify everything in terms of a single theory, then this would be a single symmetry, or mathematically speaking, that would describe everything. So we do know that's what happens when we write down grand unified theories or some of these higher symmetric states of the universe early on. But as the temperature of the universe drops, then these symmetries break. It's called spontaneous symmetry breaking. So what happens is this single force splits off into the 4 different forces that we have today. So that's a breaking of that symmetry that we had early on.
Okay, I'm with you now. And why do we really want to do this? Why do we need to look back to the Big Bang and before?
Well, this is something that everybody wants to know. Well, how did the universe begin? What was the starting point? And what is remarkable to me is how well we've done. The Big Bang happened 14 billion years ago, and we have a pretty good understanding of everything that went on. I mean, we have predictions for things that would have taken place 3 minutes after the Big Bang, and they're verified to incredible accuracy. But everybody's always asking, but what happened before that? Let's go farther back in time. And if only we had this theory of everything, then we hope that'll let us address some of these questions of what happened even earlier than that.
When can we see this theory to be announced? Is it likely to be soon?
Well, I would say not in the next decade. And I guess that's the fun of doing research. We don't know how long it's going to take. There's a lot of physicists working on a really interesting idea, string theory, which does have the capacity to incorporate both quantum mechanics and general relativity. But the trouble is that it doesn't seem to make predictions that we can test. So the way string theory works is that it is the most fundamental objects in the universe would be strings, and these strings vibrate, and those vibrations are particles. So one particular type of vibration would be an electron. A different type of vibration would be a proton. And it's a beautiful mathematical theory, and as yet it is not making predictions that we can see at the Large Hadron Collider. So the problem is it's a mathematically beautiful thing, but we're kind of stuck experimentally.
Does that mean we will have completed the universe?
Even if we do have a theory of everything, we still won't be finished. There's always the chance of looking further back in time. The more we know, there's always more questions that appear. Humans are really creative people, and we are explorers. It's fun. We want to go into the unknown. So there will always be new questions for us to ask.
Why is it called the theory of everything then, if it's not going to be describing everything?
That's a physicist's word for the unification of all the forces. And automatically, if you're unifying the forces, you'll probably understand what the universe is made of, which right now we don't. We only know 5% of the total content of the universe, the ordinary atoms. We don't know the dark matter. We don't know the dark energy. So when physicists use this term, theory of everything, what they're referring to is the unification of the 4 forces and the understanding of the content of the universe.
Thank you very much. That's Catherine Fries of Nordita. That's the Nordic Institute for Theoretical Physics.
And finally, it's time for our question of the week with Amy Goodfellow. She's been tuning in to find out the answer to Dave's query.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
Why does a minor key sound mournful and a major key happy?
We, along with Sophia Pang on Facebook, are anxiously waiting for an answer to this one. I was thinking of making a new Naked Scientist theme tune, and I'd like it to be happy and exciting, not sad. Music psychologist Dr. Andreas Giavio is here to help. Firstly, Andrea, is it true that music can make us feel in a certain way? Or is it just me being an emotional person?
That's a very interesting question. Most people would agree that music makes us think certain things or feel certain feelings, but actually not everyone would agree on how exactly these thoughts or feelings are generated. Most importantly, it seems there is no way to prove that what the question really implies, that there is a specific relationship between a certain type of musical chord and a certain emotion, really occurs universally.
Okay, so there's a lot to take into account. Let's start at the beginning then. What are we actually hearing when we listen to music?
Well, unless we really want to focus on them. In our everyday musical experience, we do not really listen to chords as such, but rather we listen to durations, dynamics, timbres, lyrics, and many other musical parameters. When we listen to someone talking to us, for example, we do not really focus on the letters that make the words, but we rather rely on a broader context, the sentence, the gestures, the way we feel about that person, and so forth.
Right, there's a whole host of things that we are hearing when we listen to music. But you mentioned earlier that there's no way to prove that what I would consider a sad note is what someone in, say, China would also consider to be sad. Why is this?
Mainly because a clear distinction between major and minor keys only emerges within modern Western musical system and is not consistently adopted in other musical cultures and traditions. This is why a number of researchers now tend to consider enculturation as a good way to look at the issue.
Enculturation? What's that?
Enculturation is basically where you learn an association between two unrelated concepts by constantly being exposed to that association. For example, we might link certain features of music, such as a minor key, to certain meaningful contexts, like a funeral march. So this means that we tend to develop relationships in our engagement with music within our own culture, leading to predictable emotional correlations and meanings.
So it's a learned association that means we, here in the West at least, think minor keys sound more sad.
Well, while our lifetime of listening experiences certainly plays an important role, it might be a bit oversimplified to attribute our emotional experience of music solely to such learned association. Other theories, for example, found commonalities with emotional cues in language, arguing that, as a sad speech, minor keys may sound sad because they tend to be less stable and have lower notes than normally expected. So, in the West at least, we do think of minor keys as sad and major keys as happy, because we have learned to associate these sounds with sad or happy experiences, including language and our interactions with others.
So if people all across the world are listening to our Naked Scientist show, there might be no music that I could use for a new theme tune to make everyone feel happy and excited. Maybe let's just stick to the current tune then.
Thanks, Amy. I'm Sam Mahaffey, and next week I'll be trying to answer a question that Llewellyn tweeted us.
Why do we have toenails?
What do you think? Tweet at Naked Scientists or join in the debate on the forum, thenakedscientist.com/forum.
That just about wraps up this week's show. Many thanks to our producer, James Farr. Next week is a special edition of The Naked Scientists. I'm delving to the outer reaches of our solar system to see what the New Horizons probe has discovered and what's beyond our beloved Pluto. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Greer Jackson. Thank you very much for listening. Goodbye.